Yes, welcome back. Here I am going to explain fourth example based on variable separable method. Let's see. Use separation of variables to solve 4ux plus uy is equals to 3u. Here ux is nothing but dou u by dou x, uy is dou u by dou y. Therefore, here u is the dependent variable and x and y are the independent variables. Okay, with u of 0 comma y is equals to 3 into e power minus y minus e power minus 5y. This is the given condition. Okay, so whenever they are giving this type of condition, see here x value is 0 and the RHS expression contains two exponential function. Then how to solve this type of problems? So it is very important example. Let's see. The given differential equation you just rewrite and take it as equation 1, and condition you take it as equation 2. Okay, now let us write the solution here based on dependent variable u and independent variables x and y. Therefore the solution is u of x comma y is equals to x of x into y of y, equation 3. Okay, now let us find dou u by dou x and dou u by dou y values with the help of equation 3. Now let us differentiate equation 3 partially with respect to x. Okay, therefore x dash of x is x dash of x into y of y. Take it as equation 4. Now differentiate equation 3 partially with respect to y. Therefore dou u by dou y is equals to y dash of y x of x. Take it as equation 5. So use equation 4 and 5 in equation 1. Therefore your equation 1 becomes 4 into x dash of x into y of y plus y dash of y x of x is equals to 3 into x of x into y of y. So here you are having 3u. In place of u you are writing equation 3. Okay, in place of u write x of x into y of y. So therefore RHS side you are getting this expression 3 into x of x into y of y. Now let us rewrite this expression. So you send y dash of y into x of x to RHS side, then it becomes 4 as it is, x dash of x into y of y as it is. If you send second term to RHS side, it becomes 3 into x of x y of y minus y dash of y x of x. Here in these two terms x of x is common. Okay, so LHS term as it is. In RHS term, if you take x of x common, the remaining terms are 3 into y of y minus y dash of y. Okay, now if you rewrite this, 4 into x dash of x y of y is equals to, here let us take minus outside. Okay, if you take minus sign outside, then you are getting x of x y dash of y. So this takes the minus sign, therefore minus 3 into y of y. Okay, now you separate the variables, x at one side, y variables at one side. Then x variables are this x of x you send it to LHS side, y of y to RHS side, then it becomes 4x dash of x by x of x is one differential equation. Similarly minus y dash of y minus 3 into y of y divided by y of y. This is the second differential equation, ordinary differential equation. Okay, LHS is function of x and RHS is function of y. Now let us equate these two differential equation to some constant lambda. Okay, then now let us solve this. Here we are not solving independently because they are given some condition. See how to solve this example. So after up to here you know we are equating to some constant. So after this, while solving these two, okay, so let us consider first differential equation is equals to some constant, that is 4 into x dash of x divided by x of x is equals to lambda is equal equation 6. Now this second differential equation you take it as equation 7. Okay, then we are using both the equations here. Equation 6 I am rewriting here. Then if you rewrite this, 4 into x dash of x is equals to lambda into x of x. Okay, then 4 into x dash of x is equals to this term, if you send it to LHS side, it becomes negative lambda into x of x is equals to 0. So just same equation 6 we are writing in this pattern. Okay, now you take it as equation 8. Now the equation 7, so this is your equation 7, you just rewrite this equation 7. Therefore you are getting y dash of y minus 3 into y dash of 3 into y of y is equals to minus lambda into y of y. This minus sign and y of y you are sending to RHS side. Therefore you are getting this expression. Okay, then if you rewrite this y dash of y as it is minus 3 into y of y as it is, take this RHS term to LHS side, it becomes plus lambda into y of y is equals to 0. Then here in second and third term y of y is common, you take it, then y dash of y plus, okay, here plus means here let us start with here y of y is common, then here remaining term is lambda, here remaining term is minus 3. We can write y of y into lambda minus 3 is equals to 0. So this one you take it as equation 9. So this is your equation 8. So equation 6 you are rewriting in this format and you are taking as equation 8, and equation 7 just you are simplifying and you are writing in this format. This is your equation 9. Now let us use equation 8 and 9 to get the solution. Okay, here two solutions we are getting. Okay, let us see here. Consider the given condition. They are given condition with the example itself. When x is equals to 0, u is equals to 3 into e power minus y minus e power minus 5y be the solution of 9. Okay, so let us assume here this is the given condition in the example. This is the solution of equation 9. Okay, by comparing this solution, so this solution is valid only when x value is 0. So when they are giving this type of conditions, because RHS side this expression contains two exponential function, then here we need to extract two lambda values. Okay, so how to get two lambda values? Let's see here. First term is 3 into e power minus y. E power minus y means here you compare with e power minus lambda y. Okay, so suppose it is e power minus lambda y means here lambda value is 1, right? So coefficient of y is 1 here. Therefore first we are choosing 1. Coefficient of y is 1. You are neglecting a negative sign. The same way here second exponential function. Here e power minus y minus 5y. Coefficient of y is 5. Okay, you remember this. So using this coefficient of y here in first term is 1 and coefficient of y in second exponential term is 5. So here 1 and 5. Using this 1 and 5 and using equation 9. In equation 9 it contains the constant lambda minus 3. So we are getting two lambda values. Let's see how it is. So case 1 we had to choose from equation 9, we are choosing lambda minus 3. Okay, then because lambda minus 3 is the constant term in equation 9. So let us consider equation 9, and in equation 2, equation 2 is nothing but your condition. From this condition you just go with the first part. First part is 3 into e power minus y. Minus y means here y coefficient is 1. So now you equate lambda minus 3 is equals to 1. Therefore lambda is equals to here 4. Lambda value is 4. You got one lambda value, lambda is equals to 4. In the same way, okay, let us solve this first. Means here case 1 is valid when lambda is equals to 4. Similarly we are proceeding with the case 2. To get case 2 lambda value, see here we are using second term. Second term is e power minus 5y. So therefore coefficient of y is 5. Now in place of 1 you are writing 5 to get case 2. So if you get if you write 5 here, lambda is equals to 5 minus 3, right? Lambda minus 3 is equals to 5. Therefore lambda is equals to 8. So lambda is equals to 8 is the second case. Lambda is equals to 4 is the second case. Only thing is you need to understand here how to get lambda values. To get lambda values, once again I will explain the concept here. We are using equation 9. So in equation 9 the constant term is lambda minus 3, and in the given condition choose the first term. First term gives 1 lambda value, second term gives 1 more lambda value. Using first term, coefficient of y is here 1. Therefore equate lambda minus 3 is equals to 1. You are getting lambda is equals to 4 is the first case. Then in second case, to get second lambda value, here use the coefficient of y is 5. Then if you use lambda minus 3 is equals to 5, therefore lambda is equals to 8. Lambda is equals to 8 is the case 2. Okay. Then let us move by taking lambda is equals to 4. Case 1, how to solve, how to get the solution. Okay. Now you see here lambda is equals to 4 is the first case. So now use equation 8 and 9. So in equation 8, wherever lambda is there, you substitute 4. Therefore you are getting 4 into x of x minus, so 4 into x of x is equals to 0. This 4 you are getting due to lambda. Okay. Then in place of lambda, if you substitute 4, you are getting this expression, equation 8. Okay. Your equation 8 becomes 4 into x of x minus 4 into x of x is equals to 0. Then send this term to RHS side, then you are getting 4 cancels, x of x divided x dash of x divided by x of x is equals to 1. Integrate on both sides with respect to x, then you are getting log x is equals to x plus c. So you send log term to RHS side, x of x equals to e power x plus c. Split this exponential function, x of x is equals to e power x into e power c. So take new constant in place of e power c. New constant is a1. Therefore x of x equals to a1 into e power x. Therefore the final solution x of x equals to a1 into e power x. This is solution, that is x of x. Similarly you get y of y value by using equation 9. In equation 9, where is lambda minus 3? In place of lambda use 4. Therefore y dash of y plus y of y, lambda minus 3 means you are writing 4 minus 3 is equals to 0. Y dash of y, 4 minus 3 is 1, therefore you are getting y of y is equals to 0. Send y of y to RHS side, y dash of y is equals to minus y of y. Okay. Then y dash of y divided by y of y is equals to minus 1. Integrate both sides with respect to y. Okay. Then integration of LHS side gives log y of y is equals to integration of 1 gives y. Okay, minus y plus c. Then send log to RHS side, y of y is equals to e power minus y plus c. Split this exponential function, e power minus y into e power c. In place of e power c, use the new constant b1. Okay. Then y of y is equals to b1 into e power minus y is the solution of second differential equation. Equation 10 is the solution of one differential equation, and equation 11 is the differential equation for the second one. Okay. Now let us write the final solution. U of x comma y is equals to, in place of x you are writing a1 into e power x. In place of y of y you are writing b1 into e power minus y. So a1 into b1, if you combine these two exponential function, you are getting e power x minus y. Okay. Then the final solution, u of x comma y is equals to, in place of a1 b1, let us use new constant c1 into e power x minus y. This is your solution, complete solution for the first case. So if you want better, you take it as u1 of x comma y. This is only first part. Okay. u1 of x comma y is equals to c1 into e power x minus y. This is equation 12. Now case 2. In case 2 again we are getting lambda value, one more lambda value, as I explained earlier. Here lambda minus 3 is the constant in equation 9, right? And in the given condition, if you take second exponential function, their coefficient of y is 5. Therefore lambda minus 3 is equals to 5, lambda value is 8. When lambda value is 8, then you need to solve again equation 8 and 9 in the same pattern. So in place of lambda, use 8. Okay. Then you are getting 4 x dash of x is x dash of x minus, in place of lambda you are writing 8 into x of x is equals to 0. Then send this term to RHS side, 4x dash of x is equals to 8x of x, 4 ones are 4 twos are, then you are getting x dash of x divided by x of x is equals to 2. Integrate on both sides. Integration of LHS gives log x of x, integration of 1 gives x plus c. Okay, then send log to RHS side. X of x equals to e power 2x plus c. Split this exponential function. In place of e power c, use constant a2. Then x of x equals to a2 into e power 2x. Now you take this solution as equation 13. Now go for second, equation 9. In equation 9, in place of lambda, we are using 8, second case. Okay, y dash of y plus y of y, 8 minus 3 gives 5. Then you send this term to RHS side, it becomes y dash of y is equals to minus 5 into y of y. Now if you rewrite this, y dash of y by y of y is equals to minus 5. Integrate on both sides with respect to y, therefore you are getting log y of y is equals to minus 5y plus c. So send this log to RHS side. Y of y is equals to e power minus 5y plus c. Split this exponential function. In place of e power c, use notation b2. Therefore y of y is equals to b2 into e power minus 5 is your equation 14. Okay, now here also you got x of x and y of y. Once again you rewrite the complete solution. U of x comma y is equals to a2 into e power 2x and b2 into e power minus 5y. You combine these two exponential function, then e power 2x minus 5y and a2 into b2. In place of a2 b2, use the new constant c2. So for this you better to take the notation u2 of x comma y, because this is second part of solution. u2 of x comma y is equals to c2 into e power 2x minus 5y. Now you got two solutions. One is from equation 12. Equation 12 is the first part, case 1. Then equation 15 represents the second part of the solution. Now you combine those two solutions, u1 and u2. Therefore you are getting u of x comma y is equals to, first part solution is c1 into e power minus x minus y, plus second part solution u2 value c2 into e power 2x minus 5y. Okay, and you take it as equation star. So this is the final complete solution of given partial differential equation. Whenever they are giving the condition, so if the condition consists of two exponential function, so you need to solve in the same method. Okay, this is the solution. Okay, then let us use the given condition to find the constants. Okay, when x is equals to 0, so they are given condition when x equals to 0, u of 0 comma y is equals to 3 into e power minus y minus e power minus 5y. This is the given condition, and your latest equation star is the final solution. In equation star, substitute x is equals to 0 in equation star. So e power 0, therefore here you are getting e power minus y. Okay, here in place of x 0 means e power minus 5y. Okay, compare these two equations. So LHS side you are having same when x equals to 0. LHS side is same expression, u of 0 comma y. Here also u of 0 comma y. If you compare RHS expression, in place of c1 you are having 3, in place of c2 you are having minus 1. So therefore this condition is useful to find the constant. Here c1 value is 3 and c2 value is minus 1. Substitute c1 and c2 values in equation star. Therefore u of x comma y is equals to, in place of c1 3 into e power x minus y, in place of c2 minus 1. Therefore minus e power 2x minus 5y is the final solution of a given partial differential equation after replacing the constants. Okay, so thank you for watching this video. So in next video I am going to explain one more example. Thank you.